Let's use an example from the textbook now to go over the process of hypothesis testing. On page 2 of the text, we have a scenario which pertains to coffee consumption and blood pressure. Remember, step 1 is to state the research question and hypotheses. The scenario here would like to investigate if there is a relationship between the number of cups of coffee consumed each day and blood pressure. The text is hypothesizing that people who consume more coffee will have higher blood pressure. Note the difference between the research question and the research hypothesis. One poses the question and the other states a prediction about the question. We will now conduct a hypothesis test to test this hypothesis. No, that's a tongue twister. Let me repeat that. We will now conduct a hypothesis test to test this hypothesis. Naturally, we need to collect some data. The text tells us that our population of interest is people living in Australia. We are told that we are going to recruit 40 people randomly from this population. We then select a testing day and ask each participant, here IDs are for people from 1 to 40, to record how many cups of coffee they consumed that day. At the end of the day, their blood pressure is measured by the researcher. Once the data is collected, we have to calculate the appropriate test statistic and the associated p-value. The problem, though, is which test would be the most appropriate to use in order to obtain this test statistic. Now, there are a lot of statistical tests out there, each one with a different use and different purpose. What we need to do is consider what type of variables we are dealing with, as well as the research design. Remember that we are looking at the relationship between number of cups of coffees consumed and blood pressure. Remember that the hypothesis was that, more cups of coffee will result in a higher blood pressure. More of this means more of that. So what tests that we've covered before can we employ here? If you had said correlation and regression, you are correct. Don't worry if you can't remember them all now. The second half of this lecture is designed to refresh your memories on some of the more common tests that we have covered. For now, let's just look at this particular output. The test statistic for the correlation between these two variables is given by the R value, or the correlation coefficient. Here, R is equal to 0.416. This tells us that the relationship between number of cups of coffee and blood pressure has a weak positive linear correlation. Remember that the value for R can range from 0 to 1 for positive correlations and from -1 to 0 for negative correlations. The closer the value is to 1 or -1, the stronger the relationship. The actual value itself represents how closely the data values fit on the regression line, this particular line here. For this example, they're quite spread out. They aren't all exactly nicely fitting on this line, which is why the relationship is only 0.416. More on this next week when we review correlation and regression. But for now, we have computed the test statistic that we need. SPSS has also given us the associated p-value for this test statistic. In this case, it's 0.008. Now, we need to compare the p-value of 0.008 to the significance level. Remember that the p-value is a probability which can range from 0 to 1. Try to visualize it on this number line. That's what I do anyway. Depending on where it exists, we can determine immediately whether or not our results are significant. But what would be the significance level? If the question or scenario does not specify a significance level, we naturally assume it to be 0.05. Now this value is quite arbitrary, and I'll discuss why it's set at 0.05 next week. So our significance level is set at 0.05, highlighted in blue. I'm just going to put in some numbers so we can visualize the number line a bit more clearly. I chose to use a scale which increases in increments of 0.025. However, this is for visualization purposes only. I'll also highlight all the values less than our significance level of 0.05 so that it paints a clearer distinction between significant and not significant. So, where on our number line does our computed p-value lie? Remember, the p-value is 0.08. Let's visualize it with this green line. 0.008 is less than 0.025, but larger than 0.01. It's probably going to be here somewhere. Regardless of where it lies, all I need to know really is that it's less than the significance level of 0.05 and that it lies within my significant range, indicating to me that the results are significant. The final step, of course, is to make our conclusion. We have found a significant relationship between our two variables, number of cups of coffee and blood pressure. But does this mean that there is a relationship within the population? Here's our output with the test statistic and p-value once again. The correlation value here is 0.42. This indicates that people who consume more coffee tend to have a higher blood pressure for our sample. The p-value indicates that this R value, this correlation coefficient, is significant. P is 0.008. This suggests that we actually can infer the results of this sample to the population. In other words, within the population of interest, people who consume more coffee tend on average to have a higher blood pressure. As a summary for hypothesis testing, we are trying to address a research question or research hypothesis about a population of interest by using sample data. There are many varieties of hypothesis tests, each with their own test statistic, but the steps and processes for each are essentially the same. We compare the evidence of the test statistic to that of the level of significance.